So, as mentioned, I'm Stephen Slupsky. I'm CEO of Scanimetrics, and we've been in this sort of predictive analytics and technology space for a while. We started out in 2001 in kind of with a focus exclusively on wireless technology and wireless sensors, and we started off designing and building really, really tiny wireless devices that actually went into other chips to test these things and validate their performance while they were being manufactured and built. But by 2008, and the economic changes that happened as a result of the financial crisis and whatnot, that was our first opportunity to kind of go beyond that particular area of technology and into a market space that was related to the mining industry. And we started working with some of the oil sands companies in Alberta in this whole space of structural integrity and structural health monitoring. And so we took our technology of wireless sensors and whatnot, and we started applying it to mining equipment and trying to resolve some of the reliability issues that they were having with their equipment. And they've got notable issues in the oil sands that are similar in a lot of ways to what hard rock mining sees, but in some other ways they're quite a bit different. But by about 1 to 2 years into that sort of new space, we started to notice another sort of characteristic, and that was the customer, while they initially kind of expressed this need to be able to monitor and collect data, what we observed about the behavior when they got this data is that they did nothing with the data. It would sit on a computer or a hard drive literally for months on end until somebody got around to actually looking at the data and doing some analysis. So we quickly understood that there was a need to do more with than just produce data, to be more than just a data source, and that you actually had to reduce the data into information that people could make decisions of. So the second part of what we started to do at that time was there's this emerging technology that was developing to deal with big chunks of data. So this whole big data term or coin that you might have heard. And so we really became experts of analyzing large buckets of data, and in this particular instance, the collections of data we were analyzing were enormous in size, gigabytes leading up to terabytes of data that you had to sift through and find little snippets of information that were telltale signs of things. So what I've done today is I put together a presentation that really talks to a bunch of examples of where we've deployed this stuff and actually used it, and what some of the information you can get out of this data, and what we believe the meaningful use of this data to industry, particularly the mining industry, is. But there's also other related industries and other industries that can use this. So, first I'll just talk a little bit about what predictive analytics is, and it's this idea that we can extract information from data. And so all our companies have got all sorts of data sources, but limited ability to actually generate useful information from that. And many companies have just huge amounts of data, but limited understanding of how to reduce that to useful information. This predictive analytics space is based on typically statistical techniques that come from modeling, from machine learning and data mining techniques that have evolved over the last number of years with the rapid advancement of computer technologies. And it's really focused on uncovering or identifying relationships between sort of what we call explanatory variables and predictive variables that are based on past occurrences and things like that. And by using that information and understanding and identifying those relationships and correlations, you are able to predict trends and behaviors and future events. So who's using this? And a lot of companies, particularly in the tech space, have started to really adopt these predictive analytic techniques, and they've driven the maturation of the whole industry. So you'll see a lot of online retailers and companies use this for managing their customer relationships, for direct marketing, for upselling when you're on their web store. Miraculously they come up with some product, then you go, oh yeah, I need one of those too. And So they've invested a lot of time and energy in understanding you as a customer, tracking you as a customer, understanding what your buying habits are, and then predicting what you'll buy. And they actually, a lot of companies now do this in real time. So as you're on the site and you're making your buying decisions there, you'll see targeted ads start to show up on you and display to you on things that they think you're likely to buy. And so they're using these techniques to make those predictions on your buying habits. We're seeing doctors start to use this technology in clinical decision support systems. So now when they do diagnosis, they'll go to a computer and they have these intelligent systems that help them weed through all this very difficult diagnostic information and help them make better diagnostic decisions. Financial institutions and insurance companies and governments have been using the technology for fraud detection. So you ever wonder why when you go to the store and try to use your credit card and it's been cut off, and you're going, well, I just used it like half an hour ago. What's going on here? The ability of these fraud detection technologies to detect fraud on your account are really lightning fast now, and they can shut your account down in a matter of minutes when they detect this stuff. And insurance companies are using it for underwriting, for doing risk management, assessing risks, and then making decisions on policies and things like that. So we're seeing a lot of use on a lot of different areas of our economy and our personal uses and our health. My focus is in two related areas to mining, which are structural health and process improvement. And so we've done work on showing relevance to things like haul trucks and shovels, conveyors and crushers, rocks, bolts, and just any old bolt, pipelines, flanges, and valves, and things like that, as well as process improvement. We're working, this is a kind of a new area for us to get into with our technology, but looking at actually measuring an in situ gold heap leach process and then helping to enhance the recovery of gold from that process. So with regards to structural health and process improvement then, so I've just kind of given some examples of what these explanatory variables and predicted variables might be. So examples of explanatory variables might be things like strain, tension, load, vibration, material loss. These are things where there's sensors and there's technology out there that allows you to actually do direct measures of these things and actually record that as data. Things that are derived from this data are things like fatigue. You can look for patterns in that data that might tell you something about the cycle time of a particular piece of equipment, its operating time, and other conditions of the equipment. And then there's sort of the environment of the equipment itself. There's, its geolocation, its temperature, the time it's being used, if it's raining, the moisture, the pressure, and other sort of environmental things that affect the equipment and have an impact on that. Examples of predicted variables that you could use, and conditions you could predict from that information, future events, are things like cracking, wear, failure, stability, safety and risk management related issues, compliance, regulatory compliance, environmental compliance, and then things related directly to productivity and efficiency. So what I'll do is I've got the two sets of examples. I'll deal mostly with a bunch of structural health applications, and I'll talk about the process improvements at the end. And I'll start by saying that this is a really difficult task in the mining industry. It's difficult because failures have huge consequences. You're dealing with large sums of or large volumes of data. The different groups within a mining organization have different uses for data and make decisions based on different uses of that data. Historically, it's been difficult to actually even just generate this data because the technology wasn't advanced enough to actually make this either cost effective or simply doable. But the big change particularly in the last 5 to 10 years has been the advent of really the smartphone. The ability and the thing about the smartphone that's really enabled this is the power consumption. We don't really think about that in their day-to-day life, about, this thing lasts for days on a single charge. But it's that capability and all the investment and work that's been done to create components that go into a smartphone that make it last for days on a single charge. And by taking that technology and then adapting it to these mining applications, we can make sensors now that you can stick onto equipment, and you can literally monitor this equipment for years at a time without having to change batteries. So it makes maintenance of this equipment and these sensors much, orders of magnitude easier to do, and simplifies the job of creating the data streams in the first place. So with that in mind then, I've got a bunch of slides here now where I'll talk about some of the problems that we've addressed directly with some of this technology and what some of the outcomes of this are. This particular example is a jaw crusher that is experiencing a bunch of reliability issues, and there's concern that if this jaw crusher stops working, that have a very big impact on productivity and production.
We met at Lausanne School, a mining day put on Innnovation, and listening to what he said about these remote wireless sensors, we thought we'd put it on our plant, which you see pictured there at Manchester. And then it evolved to another project. But I just wanted to say that you pick up ideas and just apply them, and they're not expensive. And you can have unpredicted and very pleasant results coming out.
Yeah. And so in this particular example, we had these issues, to go down there and look, and you can't really see it in this picture, but a lot of the maintenance activities that go around this, people were welding on all sorts of additional metal and steel to fix problems around cracking and whatnot of the jaw crusher. And so we got the call from Rob, and he said, well, why don't you come down and stick a bunch of sensors on this thing and tell us if there's something we can do to our maintenance and how we operate this equipment to prevent a catastrophic failure. And so we did. We went down and we surveyed the equipment, identified a bunch of key locations on this equipment to actually install some of these sensors. And there are these wireless sensors. We just kind of stick them on here and there. And we have a system that actually lifts this data from the sensors that form in a wireless network. We get them onto the internet. They end up in our cloud. And then from there, we can do all this data analytics and big data analysis on these data streams. And so what we found over the past number of months that we've started to do this analysis is that there are some underlying issues with the foundation and how the equipment's actually supported, and that the frame was actually twisting from time to time, and that at certain times we saw marked increases in the amount of twisting that was happening to this frame. And then we started looking at some of these environmental conditions, so the rain and other factors that were potentially correlated to some of this stuff. And what we believe we found is a correlation between the amount of rain, the action, and the amount of vibration and strain that's exerted on the machine seems to be correlated when you have large rainfalls. And you get subsidence of the foundation, and then you get gaps between the supporting material and the actual machine itself, and then it starts twisting, and the cracking and the damage accelerates. And so by doing simple things like just shoring up the foundation a little bit and not necessarily welding more stuff onto the machine, but it's the shoring up of the foundation actually dramatically reduces the amount of fatigue that the machine experiences, and of course lower fatigue allows us to expect a longer machine life, and so that's the outcome for that kind of activity. Another example, we worked with a coal mining company and a supplier of sort of aftermarket equipment to shovels. This particular company, I think based in Kelowna, makes saddle blocks that go on P&H shovels, and they had problems. The owner of the equipment that was operating the mine had problems with the OEM equipment. The saddle blocks were cracking, and they were running these things, and it just created all sorts of havoc for their production schedule. The cost of replacing these things was enormous, the amount of time it took, and if they left it too long or they did this stuff wrong, it actually affected the boom, and it could get extremely expensive. So the idea was, this particular aftermarket guy had was, well, I can build a better saddle block, and I can do that by making it so that the saddle block shears, like the bolts connecting the saddle block to the boom actually shear before the saddle block bends or wrecks the boom. And so they redesigned the saddle block. We put some sensors on the saddle block, we measured these forces, and then they went off and redesigned their saddle block to actually incorporate these shear bolts instead. So the idea is you run your saddle block, and eventually it's the bolts that fail, not the saddle block. And it takes maybe an hour or two to replace the bolts, and you're down for an hour or two, versus if you wreck the saddle block, you're down for days and maybe months if they don't have one in stock and you got to order one and all that kind of stuff because of inventory issues. So that's a big that's a big deal for the vendor, for the aftermarket vendor, but it's also a big deal for the OEM and for the operator, the owner of the equipment. And so the output from this is to repair, reduce their repair time and repair costs, their interruptions to their production, to prevent actually damage to the block and or the boom itself. And then we use the data from the sort of the ongoing monitor to actually do additional stuff and analyze things like the total damage to the machine, the ongoing damage from other factors such as operator behavior and stuff like that. So there are a bunch of other detailed data you can get out of the analytics, and that'll become a little bit more apparent in the next set of slides. So in this case, this was another construction company, and they operated a number of these Hitachi EX1200 excavators and shovel, and they were having a lot of problems with cracking of their boom. They didn't understand why they were cracking, but they knew that it was a big problem, and they would re-weld, and then a few months later cracks would reappear, and it seemed like they were chasing their tail on this a lot. So we installed a bunch of sensors on their boom, both strain sensors, so that we could measure strain and derive fatigue from that. But we also measured put a bunch of crack sensors on this thing to actually measure when this stuff cracked, and then to correlate this information. And what we found was that and sometimes at 2 o'clock in the morning, operators would take the shovel and they would then start banging it on the ground. And so we asked them, well, why are they at 2 o'clock in the morning banging the shovel on the ground? Well, there's ice in the bucket, and they had to loosen the ice. So it was an operator-driven thing. People, at 2 o'clock in the morning, there's not very many supervisors around watching these guys, and it's kind of dark and all this stuff, and people just sort of, started banging these shovels. And that would lead to, massive increases in the amount of fatigue and lead to this cracking. And so we started looking at ways of slicing and dicing this information and looking at shifts and operators. And we could actually start to assign a damage index to an individual. So we could actually start to identify certain people who operated the equipment and generated more damage than another group of people. And so that gives an opportunity for companies to do retraining, to investigate that, find out, what are the underlying reasons behind that increased fatigue or damage to the equipment, which is something you can't normally measure. I mean, most of this stuff, because of our decades of sort of programmed run to there's no way to see the damage until it's done. And it manifests itself in failure and cracking. But this data, because it's predictive in nature, and it's like a gas gauge, the fatigue of a piece of equipment, if you accumulate that over a time, you know, you reach a limit of the fatigue life of the equipment and eventually breaks. And so if you visualize that as really just a gauge from full to empty, and you start monitoring that over the life of your asset, you got a pretty good idea of when that asset's going to run out of fatigue life and when you're going to start to see a massive sort of exponential increase in the amount of maintenance you do on that thing to keep the thing running. And it's not visual. I mean, this is all at the molecular level. You know, it's the micro dislocations in the underlying material that's actually causing all that cracking, and that's because of these fatigue cycles. Another application space we got involved with, this was actually one of these oil sands companies, mining companies, and they've got a really unique problem where their lifetime of their machines is typically in and around 8 years for a haul truck. And most hard rock mines, if you talk to the mines or you talk to the OEMs, they'll tell you, you know, we'll get 15 or 20 years out of a haul truck in those applications. And so the oil sand miners were kind of preoccupied with this idea that, gee, you know, why are we only getting 8 years life? And they were all over the OEMs, and I think they kind of patted each other on the back to a certain degree to kind of believe that, well, it's because the ground is kind of moves around on us. You know, when a haul truck starts up after it's parked beside the shovel, you know, you get this sort of wave of material as it's driving away, and they say, oh, that, you know, we're putting way more stress and whatnot. And no doubt, you know, the fact that the ground is soft and you're moving on this sort of spongy material would affect the overall reliability and the fatigue life of the machine. But I think it's also safe to say that when you understand how that's happening and why it's happening, you can use that information to actually make better decisions on how you operate that stuff. And so what we did is we instrumented some of these machines, and we again put strain sensors on these things and started looking at fatigue life of the frames in particular. And this only took, like, I think 4 sensors on the entire machine. There wasn't, you know, there was no need to put hundreds of sensors on this thing. And what we saw was some really interesting data as when we started doing the analytics on the data. And some of it was obvious. You know, we could see fatigue, we could calculate fatigue cycles, and we could do calculations on that and do predictions on what we thought the fatigue life of the frame was going to be, and look at things like FEA analysis and where the hot spots on the equipment are. But we also actually started to zoom in on some of this fatigue data, and we started to see some interesting things in the fatigue data that started to tell us some interesting things about not only the equipment it was monitoring, but equipment that it was somehow indirectly coupled to, like the shovel. So in this case, you know, we're seeing this, it's parked at the shovel, and the shovel's loading stuff into the haul truck. And you can see as it gets its first scoop and its second scoop and its third scoop, and then it drives away. And now you can actually get a lot of information from this. And it's not immediately available, but I can measure the time between these successive events, and I get a direct measure of the productivity of that haul truck and the shovel that's loading it, because I can measure the cycle time now directly of when that thing was at the shovel and when it was at the dump and when it's back at the shovel. I can measure that in time. I can also see that, you know, the operator of the shovel here isn't optimally dumping his stuff into the haul truck, because we're getting this massive fatigue cycle at the leading edge of this thing. So he's dumping a little bit too high, and it's causing a big, huge amount of strain on the thing instead of setting it in there in a little bit controlled manner. So again, through some operator training, you can you can train your operators to reduce the magnitude of that leading peak there, which reduces the amount of damage you're doing to the truck, that the shovel's doing to the truck. By measuring summing up all these loads, I can tell you how much payload that particular truck is hauling, and again, that's directly related to your productivity of that particular machine. And so there's a lot of really interesting information when you start to actually analyze this data and get into the analytics of it. We worked with another company on a rod mill. So they've got a rod mill. It's got a liner in there. The liner is bolted to the shell, and it rotates, and the rods move around inside there and crush the ore. So this particular company had a lot of failures of the bolts that fasten or hold the liner to the shell, and they got to the point, I think, where they're replacing a lot of these bolts every 60 days or something like that, or all of them every 60 days, because they were randomly failing, and if too many of these things popped off, they had to shut down. And so the idea here was to actually measure the fatigue on the bolts and to try to understand what the problems were. So going into this is an example of one of the bolts, and this is one of the ones that broke, and kind of shows you, kind of how it broke off. And some of the obvious things going into this were, do you have bolt defects that are causing these things to break? Is it a problem with the liner design, the speed at which they're running the mill, other operating conditions? So we did some work, and we outfitted not all of these bolts, but some of these bolts with some sensors that would allow us to directly measure the tension in the bolt. Because we knew going into this, some work we'd done on some other bolt-related applications, is that when you torque a bolt, you don't really know what the tension in that bolt is. You think you kind of know because you make some assumptions on what the friction of the threads is, and you've got a torquing procedure that you think kind of sets the tension in the bolt. But the really important thing for a fastener is the tension, the load it's under, not the actual torque. And so because sometimes a lot of these assumptions are wrong, the tension in the fastener is completely wrong as well. And so what we found in this particular case, that indeed that was the case, that many of these fasteners were, maybe at 1/3 what the tension was supposed to be. So they were all following their bolting procedure, their published procedure of how to torque that bolt. But you can see, and we've seen this in many other industrial applications, the actual load on that fastener was 1/3 of what it was actually supposed to be. And of course, when that happens, and then you put it into operation, the fatigue accelerates, the loss of tension accelerates, and then you get failure and bad things happen. So we found that in this case, but we also found that some bolts, didn't matter how much you torqued them, they kind of plateaued. It kind of suggested to us that there were a number of bolts that were being used that were actually defective coming in, so that they needed to implement some sort of incoming inspection on these bolts and kind of test some of these bolts before they actually put them into production and started using them. And then we were in the process of kind of discussing this, but you can imagine it's kind of difficult for companies to jump and say, well, monitor all the bolts, because we really think it's important that they do actually monitor all the bolts on this thing. But we think the best outcome is to actually monitor all these bolts and then to optimize your maintenance cycle. So instead of shutting this thing down on a sort of a preventive maintenance schedule where you shut it down and you sort of blindly replace all the bolts, if you kind of know ahead of time, because you've measured the stress in all these bolts, and you know ahead of time which ones have fatigued and which ones haven't, your job of replacement now is 1/10 of what it probably was, because there probably only 10% of the bolts need to be replaced. So you can shut down, replace 10% of the bolts, and then be up and running again within hours, instead of being shut down for days, replacing all of the bolts. And so that the cost of that additional production is millions of dollars. And so the return on investment for doing that is enormous. But it does cost it does cost money to put the sensors on there, and that's a bit of a hang-up in our current economy, to get people to spend a little bit of money. But the benefits are profound.
How are you measuring it? How do you calculate the tension? Like, you tell the change in tension from compression and how much the compression changes. It's a strain gauge.
Yeah, it's just a strain gauge.
How do you actually know the tension of the bolt off the strain gauge?
Oh, there's a direct correlation. Once you know the strain, you can calculate the elongation of the bolt, and then
How do you calculate that in the first place?
how do you?
How do you relate the correlation to strain in the first place? What's the
Oh, just need to know the material the size of the bolt and its material properties. So the grade of bolt, grade 8, grade 9, grade 7, whatever the bolt is. And so once you know the grade of the bolt and you know the dimensions of the bolt, there's a very straightforward mathematical.
Untorqued, and then you torque it.
Right.
And as you're torquing it up, you're measuring that elongation curve.
Exactly.
And that's how you calculate it. Not during the torquing operation itself is when you're calculating the tension on the bolt.
Exactly. Yeah.
Okay.
Yeah. And so if you look back at this here, this is showing the torquing procedure, and then actually this is an operation, but you're seeing here the relaxation in the bolt during operation.
It was the calculation of the
Yeah.
tension in the first place, and you're measuring it while you're torquing it in the first
Right.
place.
Exactly.
That's what I was.
So we get a good direct measurement between torque and tension, and of course, since we know what the tension is, we can tell if the torque was right or wrong. Another application, this is Thunder Bay wind farm. They use rock anchors to hold the platforms in place. And so they drill down, several hundred feet or whatever, and embed these rock anchors into the ground to hold these massive structures in place and prevent. You imagine when the wind blows, there's an awful lot of force at the base of that wind farm. So we got a call and said, hey, can you help us with these rock anchors? Because we send guys out once every couple of years, and they'll take a crane and they'll lift the anchor until it kind of lifts off the bearing plate, and then they've got a load cell there. They measure the tension in that rock anchor, and they know if it's properly tensioned or not, or if there's something gone wrong and they need to do some remedial action. But you can imagine that's a costly experiment, or not experiment, but a costly process to do, because you got to run a crane out to site. You got to have a few people do that. It takes time, and you're only doing it once every couple of years. You can't do this on a continuous basis. So and when these things fail, you have a big problem. Here's an example of a failure when somebody was doing this procedure. They're tensioning this thing, and they didn't get the little coupling thing on properly, and it yanked on this thing, and all of a sudden there's a big crack, and you take it all off, and your rock anchor's cracked. And I'm not exactly sure what they got to do now to fix that, but I can imagine that's a lot of work, because the thing's under tension already, and they got to relieve that tension, then somehow reconstruct this rock anchor and put it under tension. So I imagine it's a lot of cost and a lot of problem for them. So we similarly took some strain gauges and installed them on these rock anchors, and we're measuring the compression of the rock anchor. So in this case, the rock anchor is already tensioned. You're installing the sensor, and then if the tension, because it's already under load, if it loses tension, it's actually going to show up as an increase in strain, because the rock anchor is under compression, and you'll relieve that compression as the tension releases. So we do that, and we've got some interesting data from that shows that we can start to see variations in the tension as the wind blows, and one side goes under tension and the other side has less tension. So you can actually see that in the data. We see where they actually broke a rock anchor already right off the bat. That was actually that cracked rock anchor. You can actually see it in the data. So there's all sorts of interesting stuff you can do with that. And we're in the early stages of that project, so there's lots of work to do on the analytics for the wind industry. So the last thing I want to talk about are some process improvement related application. And again, we're working with Rob and his group here at McEwen on at their mine site in Mexico to really understand, can we improve the recovery of gold from a heap? And Rob proposed or asked me several months ago, he says, well, can you put these sensors in a heap, and can you help me measure moisture and compaction? And at the time I was kind of, gee, I got to go inside the heap and bury these things, and it was a technical issue, but we went through a couple stages where we kind of proved out that we could actually find a way to embed these things into a heap, and we could reliably measure the moisture and the compaction, the pressure inside a heap. And as we were doing that, we were scanning the literature and looking for all sorts of information about how to validate, could this information, could we do analytics on this information and then determine a way to actually improve the gold recovery, because at the end of the day it was all about trying to increase the amount of gold extracted from the heap leach operation. And what we found is that there's quite a bit of body of evidence in the literature that suggests that, you know, if you have an optimal moisture content in your ore, you maximize the recovery of gold. And whenever you have too much leachant or too little leachant, your recovery is not optimal, and you're getting less gold, and you might be putting more cost into your heap than you need to. So we deployed these sensors and to directly measure moisture and the compaction within the heap. And so they've been actually, the initial tests were done on some columns in the laboratory, and then a second set of tests were done where they were put into a small section of the heap. We measured this data and collected this data. And what we found is that, yes, we get a good view and observation of the moisture that's actually in the heap. And then as we scanned the literature more, we found more data that suggested that the uniform application of the leachant, the cyanide solution, is, you know, really essential to having a nice optimal recovery of the gold from the heap. And so by sort of creating a grid of these sensors within the heap, you can start to visualize the interior moisture dynamics of the heap, and so we can clearly see what the fluctuations in the moisture are doing, and I haven't got it overlaid here, but we can also overlay this to rainfall, and we can show that, you know, on this particular day we had a lot of rainfall, but you can see it doesn't last for very long. It works its way through the heap within hours. That we can see the compaction within the heap, and that's important to understanding whether or not we're getting localized compaction, whether the stability on the edges of our heap is being compromised in any way. And using that information, we can make some really important decisions about how we're doing our leaching. And in this particular case, some of the immediate interventions that can be done are we can actually repair or adjust our irrigation. So we identified some locations that were being under irrigated, and they've gone off and adjusted the irrigation to address that and augment the irrigation in those particular under irrigated areas. We could also see pooling on the surface of the heap. So we can direct people that, okay, you need to go to this part of the heap, and you need to get rid of that moisture that's on the surface. It's pooling, and you're not getting the proper heap dynamics there. And then you can also rip the surface. If you've got an area that has pooled and has short-circuited the heap by creating channeling, you know, you can take a dozer in there and you can rip it to relieve that and to get the capillary action working again. And so the outcome of all this is to increase the gold recovery from the heap ultimately, and to provide an indication of the stability of that. And we're in the final phase of this particular project, which is really in the end to prove the economic ROI, which is to do this on a heap-wide basis and monitor an entire heap and then quantify the difference in the gold recovery between the two, and then to optimize the number of sensors you need to achieve that. And that's the end of the presentation. In summary, you know, the data and analytics can really make a difference to your company. I know we're programmed, you know, for decades to think run to failure, and our systems and operations are all sort of, maintenance techniques are all built up around that. But there are better ways to run our companies. There's better ways to maintain our equipment. there's better ways to keep a safe workplace and to remain in compliance with the regulators, and we just need to get get this data and do the analysis. Thanks a lot.
Thank you.